use these methods. 38. The early red LEDs were bright enough for use as indicators, as the light output was not enough to illuminate an area. Readouts in calculators were so small that plastic lenses were built over each digit to make them legible. Later, other colors became widely available and appeared in appliances and equipment. Early LEDs were packaged in metal cases similar to those of transistors, with a glass window or lens to let light out. Modern indicator LEDs are packed in transparent molded plastic cases, tubular or rectangular in shape, and often tinted to match the device color. Infrared devices may be dyed to block visible light. More complex packages have been adapted for efficient heat dissipation in high-power LEDs. Surface-mounted LEDs further reduce the package size. LEDs intended for use with fiber optics cables may be provided with an optical connector. Blue LED. The first blue-violet LED using magnesium-doped gallium nitride was made at Stanford University in 1972 by Herb Mariskar and Wally Rines, doctoral students in materials science and engineering. 39. 40. At the time Mariskar was on leave from RCA Laboratories, where he collaborated with Jacques Pankov on related work. In 1971, the year after Mariskar left for Stanford, his RCA colleagues Pankov and Ed Miller demonstrated the first blue electroluminescence from zinc-doped gallium nitride, though the subsequent device Pankov and Miller built, the first actual gallium nitride light-emitting diode, emitted green light. 41. 42. In 1974 the U.S. Patent Office awarded Mariskar, Rines, and Stanford professor David Stevenson a patent for their work. In 1972, U.S. Patent US 38199740. Today, magnesium doping of gallium nitride remains the basis for all commercial blue LEDs and laser diodes. In the early 1970s, these devices were too dim for practical use, and research into gallium nitride devices slowed. In August 1989, Cree introduced the first commercially available blue LED based on the indirect bandgap semiconductor, silicon carbide, SiC. 43. SiC LEDs had very low efficiency, no more than about 0.03%, but did emit in the blue portion of the visible light spectrum. 44. 45. In the late 1980s, key breakthroughs in GaN epitaxial growth and p-type doping, 46, ushered in the modern era of GaN-based optoelectronic devices. Building upon this foundation, Theodore Mustakers at Boston University patented a method for producing high-brightness blue LEDs using a new two-step process in 1991. 47. In 2015, a U.S. court ruled that 3 Taiwanese companies had infringed Mustakers' prior patent and ordered them to pay licensing fees of not less than $13 million. 48. 2 years later, in 1993, high-brightness blue LEDs were demonstrated by Shuhei Nakamura of Nishia Corporation using a gallium nitride growth process. 49. 50. 51. In parallel, Izumue Kaseki and Hiroshi Amano of Nagoya University were working on developing the important GaN deposition on sapphire substrates and the demonstration of p-type doping of GaN. This new development revolutionized LED lighting, making high-power blue light sources practical, leading to the development of technologies like e-Blu-ray. 52. 53. Nakamura was awarded the 2006 Millennium Technology Prize for his invention. 54. Nakamura, Hiroshi Amano and Izumue Kaseki were awarded the Nobel Prize in Physics in 2014 for the invention of an efficient gallium nitride blue LED. 55. In 1995, Alberto Barbieri at the Cardiff University Laboratory, GB, investigated the efficiency armed reliability of high brightness LEDs and demonstrated a transparent contact LED using indium tin oxide, ETO, on Algain /BAS. In 2001, 56, and 2002, 57, processes for growing gallium nitride, GaN, LEDs on silicon were successfully demonstrated. In January 2012, Osram demonstrated high power in GaN LEDs grown on silicon substrates commercially, 58, and GaN on silicon LEDs are in production at Plessey Semiconductors. As of 2017, some manufacturers are using SiC as the substrate for LED production, but sapphire is more common, as it has the most similar properties to that of gallium nitride, reducing the need for patterning the sapphire wafer. Patterned wafers are known as epi wafers. Samsung, the University of Cambridge, and Toshiba are performing research into GaN on Si LEDs. Toshiba has stopped research, possibly due to low yields. 59, 60, 61, 62, 63, 64, 65. Some opt for epitaxy, which is difficult on silicon, while others, like the University of Cambridge, choose a multilayer structure, in order to reduce crystal, lattice mismatch and different thermal expansion ratios, to avoid cracking of the lead chip at high temperatures, for example during manufacturing, reduce heat generation and increase luminous efficiency. Sapphire substrate patterning can be carried out with nanoIR print lithography. 66, 67, 68, 69, 70, 71, 72. GaN on Si is difficult but desirable since it takes advantage of existing semiconductor manufacturing infrastructure. It allows for the wafer-level packaging of LED dyes resulting in extremely small LED packages. 73. GaN is often deposited using metal organic vapor phase epitaxy, MOCVD. 74, and it also utilizes lift-off. White LEDs and the illumination breakthrough. Even though white light can be created using individual red, green and blue LEDs, this results in poor color rendering, since only 3 narrow bands of wavelengths of light are being emitted. The attainment of high-efficiency blue LEDs was quickly followed by the development of the first white LED. In this device a Y3Al5012CE, known as YAG or CEYAG phosphor, silver-doped phosphor coating produces yellow light through fluorescence. The combination of that yellow with remaining blue light appears white to the eye. Using different phosphors produces green and red light through fluorescence. The resulting mixture of red, green and blue is perceived as white light, with improved color rendering compared to wavelengths from the blue LED /YAG phosphor combination. 75. Illustration of Haigh's law, showing improvement in light output per LED over time, with a logarithmic scale on the vertical axis. The first white LEDs were expensive and inefficient. The light output then increased exponentially. The latest research and development has been propagated by Japanese manufacturers such as Panasonic and Nishia, and by Korean and Chinese manufacturers such as Samsung, Solstice Kingson, Hoyle and others. This trend in increased output has been called Haigh's law after Roland Haight. 76, 77. Light output and efficiency of blue and near ultraviolet LEDs rose and the cost of reliable services fell. This led to relatively high power white light LEDs for illumination, which are replacing incandescent and fluorescent lighting. 78, 79. Experimental white LEDs were demonstrated in 2014 to produce 303 lumens per watt of electricity, LM/W. Some can last up to 100,000 hours. 80, 81. commercially available LEDs have an efficiency of up to 223 lm/W as of 2018. 82, 83, 84, a previous record of 135 lm/W was achieved by Nishia in 2010. 85, compared to incandescent bulbs. This is a huge increase in electrical efficiency, and even though LEDs are more expensive to purchase, overall lifetime cost is significantly cheaper than that of incandescent bulbs. 86. The LED chip is encapsulated inside a small, plastic, white mold. It can be encapsulated using resin, polyurethane-based, silicone, or epoxy-containing, powdered, serum-doped YAG phosphor. After allowing the solvents to evaporate, the LEDs are often tested and placed on tapes for SMT placement equipment for use in LED light bulb production. Encapsulation is performed after probing, dicing, dia transfer from wafer to package, and wire bonding or flip chip mounting, perhaps using indium tin oxide, a transparent electrical conductor. In this case, the bond wire, S, are attached to the ito film that has been deposited in the LEDs. Some remote phosphor LED light bulbs use a single plastic cover with YAG phosphor for several blue LEDs, instead of using phosphor coatings on single chip white LEDs. 87. The temperature of the phosphor during operation and how it is applied limits the size of an LED die. Wafer level packaged white LEDs allow for extremely small LEDs. 73. Physics of light production and emission. In a light-emitting diode, the recombination of electrons and electron holes in a semiconductor produces light, be it infrared, visible or UV, a process called electroluminescence. The wavelength of the light depends on the energy band gap of the semiconductors used. Since these materials have a high index of refraction, design features of the devices such as special optical coatings and die shape are required to efficiently emit light. 88. Unlike a laser, the light emitted from an LED is neither spectrally coherent nor even highly monochromatic. Its spectrum is sufficiently narrow that it appears to the human eye as a pure, saturated color. 89, 90, all sound like most lasers. Its radiation is not spatially coherent, so it cannot approach the very high intensity characteristic of lasers. Single color LEDs. Blue LED's external video icon. The original blue LED, Science History Institute. By selection of different semiconductor materials, single color LEDs can be made that emit light in a narrow band of wavelengths from near infrared through the visible spectrum and into the ultraviolet range. As wavelengths become shorter, because of the larger band gap of these semiconductors, the operating voltage of the LED increases. Blue LEDs have an active region consisting of one or more InGaN quantum wells sandwiched between thicker layers of GaN, called cladding layers. By varying the relative in/diffraction in the InGaN quantum wells, the light emission can in theory be varied from violet to amber. Aluminium gallium nitride, AlGaN, of varying L/diffraction can be used to manufacture the cladding and quantum well layers for ultraviolet LEDs, but these devices have not yet reached the level of efficiency and technological maturity of InGaN/GaN blue/green devices. If unalloyed GaN is used in this case to form the active quantum well layers, the device emits near ultraviolet light with a peak wavelength centered around 365 nm. Green LEDs manufactured from the InGaN/GaN system are far more efficient and brighter than green LEDs produced with non-nitride material systems, but practical devices still exhibit efficiency too low for high brightness applications. With AlGaN and AlGaN, even shorter wavelengths are achievable. Near UV emitters at wavelengths around 360–395 nm are already cheap and often encountered, For example, as black light lamp replacements for inspection of anti-counterfeiting gov watermarks in documents and banknotes, and for UV curing. Substantially more expensive, shorter wavelength diodes are commercially available for wavelengths down to 240 nm. 91, as the photosensitivity of microorganisms approximately matches the absorption spectrum of DNA, with a peak at about 260 nm, UV lead emitting at 250-270 nm are expected in prospective disinfection and sterilization devices. Recent research has shown that commercially available UVA LEDs, 365 nm, are already effective disinfection and sterilization devices. 92. UV